Chapter 1. Scientific Method and the Social Sciences. During the summer that I was 12 years old, I walked 4 or 5 times a week to fish from Hingham Bridge. The distance was about 5 miles, part of it along a high railroad embankment that had been ballasted with crushed quartz. In this ballast were hundreds of quartz crystals. Each day I stopped a while to look for a perfect crystal. I found some excellent ones, but never one that could be called perfect. The books I consulted told me that a quartz crystal should be a hexagonal prism with a regular hexagonal pyramid at the end. The ones I found were invariably irregular in some way, with sides of varying sizes, frequently with several crystals jammed together so that, in seeking to share the same material, they mutually distorted each other's hexagonal regularity. After several weeks of casual searching, I found 3 or 4 crystals that were almost perfect, at least at the pyramidal end. But to find these, I had examined and discarded hundreds of distorted crystals. By what right, I asked, did the book say that quartz crystals occurred in regular pyramidal hexagonal prisms when only a small percentage of those found had such a shape? Obviously, the books meant that crystallized quartz has a tendency to take hexagonal form, and will do so unless distorted by outside forces. The fact that 99% are distorted does not deter the scientist from forming in his mind an idealized picture of an undistorted crystal, or from stating, in books, that quartz crystals occur in that idealized form. Later, when I studied science in school and college, I found that most scientific laws were of this idealized character. They were not statements of what actually happens in the world, or of what we observe through our senses, but rather were highly idealized and much oversimplified relationships that might occur if a great many other influences, which were always present, were neglected. I found that the most highly praised scientific laws attributed to great men like Galileo or Newton were of this character. It was a blow to discover that Newton's laws of planetary motion did not, in fact, describe the movements of the sun's satellites as we observe them, except in a very approximate way. In some cases, notably that of the planet Mercury, the approximation was by no means close. Still later, when my interests shifted from the physical sciences to the social sciences, and I worked with students of human society who were generally lacking in any close familiarity with the natural sciences, I found a curious situation. The social scientists usually had erroneous ideas about the methods and theories of natural science, believing them to be rigid, exact, and invariable. Accordingly, they felt that these methods were not applicable to the social sciences. Thus I found that natural scientists were quite prepared to accept as a law, a rule that was only approximately true or was true in only one case in 100, while the social scientists were reluctant to accept any rule that was only approximate or even one that had no more than one exception in 100 cases. After years of work in both areas of study, I concluded that the social sciences were different, in many important ways, from the natural sciences, but that the same scientific methods were applicable in both areas, and indeed that no very useful work could be done in either area except by scientific methods. In both areas, the laws arising from the use of scientific methods will be idealized, theories reflecting observed phenomena only approximately, but these theories must be based on our observations, and any wide failure of approximation or any totally inapplicable cases must either be explained in terms of unconsidered outside factors, or the theories themselves must be changed to cover such variant observations. The laws of historical change described in this book seem to me to fit the observed cases at least as closely as most of the theories of natural science. Most of the laws I shall mention apply, without exception, or with only slight, explicable divergencies to all the cases I know. They are then, it would seem to me, as worthy of consideration as the scientific laws on the formation of crystals. Before proceeding to examine any theories of historical change, we should review what we understand by the term scientific method. In general, this method has 3 parts, which we might call 1. Gathering evidence, 2. Making a hypothesis, and 3. Testing the hypothesis. The first of these, gathering evidence, refers to collecting all the observations relevant to the topic being studied. The important point here is that we must have all the evidence, for, obviously, omission of a few observations, or even one vital case, might make a considerable change in our final conclusions. It is equally obvious, I hope, that we cannot judge that we have all the evidence, or cannot know what observations are relevant to our subject, unless we already have some kind of tentative hypothesis or theory about the nature of that subject. In most cases, a worker does have some such preliminary theory. This leads to two warnings. In the first place, the three parts of scientific methodology listed above were listed in order, not because a scientist performs them separately in sequence, but simply because we must discuss them in an orderly fashion. And in the second place, any theories, even those regarded as final conclusions at the end of all three parts of scientific method, remain tentative. As scientific methodology is practiced, all three parts are used together at all stages, and therefore no theory, however rigorously tested, is ever final, but remains at all times tentative, subject to new observation and continued testing by such observation. No scientist ever believes that he has the final answer or the ultimate truth on anything. Rather, he feels that science advances by a series of successive and, he hopes, closer approximations to the truth. And, since the truth is never finally reached, the work of scientists must indefinitely continue. Science, as one writer put it, is like a single light in darkness. As it grows brighter, it shows more clearly the area of illumination and, simultaneously, lengthens the circle of surrounding darkness. Having gathered all the relevant evidence, the scientist may proceed to the second part of scientific methodology, making a hypothesis. In doing this, two rules must be followed. A, the hypothesis must explain all the observations, and B, the hypothesis must be the simplest one that will explain them. These two rules might be summed up in the statement that a scientific hypothesis must be adequate and it must be simple. Once again, let us confess that these two rules are idealistic rather than practicable, but they remain, nevertheless, the goals by which a scientist guides his activities. When we say that a hypothesis must be adequate and thus must include all of the relevant observations, we are saying something simple. But carrying out this simple admonition is extremely difficult. It is quite true that every scientific hypothesis suffers from inadequate evidence. That is, it does not include in its explanation all the relevant evidence, and would be different if it did so. It is not easy to tear any event out of the context of the universe in which it occurred, without detaching it from some factor that has influenced it. This is difficult enough in the physical sciences. It is immensely more difficult in the social sciences. It is likely that in any society, the factors influencing an event are so numerous that any effort to detach an event from its social context must inevitably do violence to it. The extreme specialization of most social studies today, concentrating attention on narrow fields and brief periods, is a great hindrance to our understanding of such special fields, although the fact is not so widely recognized as it should be, since any specialist's work is usually examined only by his fellow specialists, who have the same biases and blind spots as he does himself. But a specialist from one area of study who examines the work being done in some other area cannot fail to notice how the over-specialized training of the experts in his new area of interest has handicapped their understanding of that area. The second requirement of a scientific hypothesis, that it should be simple, is also more difficult to carry out in practice than it is to write down in words. Essentially, it means that a hypothesis should explain the existing observations by making the fewest assumptions and by inferring the simplest relationships. This is so vital that a hypothesis is scientific or fails to be scientific on this point alone. Yet, in spite of its importance, this requirement of scientific method is frequently not recognized to be important by many active scientists. The requirement that a scientific hypothesis must be simple, or, as it is sometimes expressed, economical, does not arise merely from a scientist's desire to be simple, nor does it arise from some aesthetic urge, although this is not so remote from the problem as might seem at first glance. When a mathematician says of a mathematical demonstration that it is beautiful, he means exactly what the word beautiful means to the rest of us. And this same element is undoubtedly significant in the formulation of theory by a scientist as well. The rule of simplicity or economy in scientific hypothesis has a number of corollaries. One of these, called the uniformity of nature, assumes that the whole universe is made of the same substances and obeys the same laws, and, accordingly, will behave in the same way under the same conditions. Such an assumption does not have to be proved. Indeed, it could not be proved. It is made for two reasons. First, because it is simpler to assume that things are the same than it is to assume that they are different. And second, while we cannot prove this assumption to be correct, even if it is correct, we can, if it is not correct, show this by finding a single exceptional case. We could demonstrate the uniformity of nature only by comparing all parts of the universe with all other parts, something that clearly could never be achieved. But we can assume this because it is a simpler hypothesis than its contrary, and if it is wrong, we can show this error by producing one case of a substance or a physical law that is different in one place or time from other places or times. To speak briefly, we might say that scientific assumptions cannot be proved, but they can be refuted, and they must always be put in a form that will allow such refutation. Other examples or applications of the rule of uniformity of nature would be the scientific assumptions that man is part of nature, or that all men have the same potentialities. Neither of these could be proved, because this would involve the impossible task of comparing all men with one another, including both past and future men, and with non-human nature. But these assumptions can be made under the rule of simplicity of scientific hypothesis or its corollary, the rule of the uniformity of nature. Thus, they do not require proof. But, on the other hand, if these assumptions are not correct, they could be disproved by one or a few clear-cut cases of exceptions to the rule. Thus, in the final analysis, these rules about scientific hypotheses are not derived from any sense of economy or of aesthetics, but rather arise from the nature of demonstration and proof. The familiar judicial rule that a man is to be assumed innocent until he has been proved guilty is based on the same fundamental principles as these rules about scientific hypotheses, and, like these, rests ultimately on the nature of proof. We must assume that a man is innocent, not guilty, until we have proof of his guilt, because it is always simpler to assume that things are not so than to assume that they are, and also because no man can prove the negative not guilty except by the impossible procedure of producing proof of innocence during every moment of his past life. If he omits a moment, the charge of guilt could then be focused on the period for which proof of innocence is unobtainable. But by making the general and negative assumption of innocence for all men, we can disprove this for any single man by the much easier procedure of producing evidence of guilt for a single time, place, and deed. Since it is true that a general negative cannot be demonstrated, we are entitled to make that general negative assumption under the rule of the simplicity of scientific hypothesis, and to demand refutation of such an assumption by specific positive proof. A familiar example of this method could be seen in the fact that we cannot be required to prove that ghosts and sea serpents and clairvoyance do not exist. Scientifically, we assume that these things do not exist and require no evidence to justify this assumption, while the burden of producing proofs must fall on anyone who says that such things do exist. The rule of simplicity in scientific hypotheses is by no means something new. First formulated in the late Middle Ages, it was known as Occam's razor and was applied chiefly to logic. Later it was applied to the natural sciences. Most persons believe that Galileo and his contemporaries made their great contributions to science by refuting Aristotle. This refutation of Aristotle, or, more correctly, refutation of Plato and of the Pythagorean rationalists, was only incidental to the much more significant achievement of making the commonly accepted rules about the universe more scientific by applying to them Occam's razor. This was done by assuming that the heavenly bodies and terrestrial objects operate under the same laws that were later enunciated by Newton. This application of Occam's razor to natural phenomena was a major step forward in making the study of nature scientific. Application of this rule to the social sciences, that is, to phenomena involving subjective factors, still remains to be done, and would provide a similar impetus to the advance of this area of human thinking. It has already been done in judicial procedure, by such rules as the assumption of innocence and the needlessness of proving negatives, and the chief task in American law, at the present time, is to protect and, if necessary, extend the application of Occam's razor to judicial procedure. Many persons in recent years have felt uncomfortable over the demand that certain persons should prove that they are not communists, but few realized that the unfairness of such a demand rests on the nature of scientific assumption and the nature of proof, and, above all, on the violation of Occam's razor. These rules about the nature of scientific hypothesis are so important that science would perish if they were not observed. This has already happened in the past. During the period 600–400 BC in the Greek-speaking world, the Ionian scientists applied these rules about scientific hypothesis by assuming that the heavens and the earth were made of the same substance and obeyed the same laws, and that man was part of nature. The enemies of science about the year 400 BC made assumptions quite different from those of the Ionians, namely, that the heavens were made of a substance different from those on earth, and, accordingly, obeyed different laws, and, furthermore, that man was not part of nature, since he was a spiritual being. They accepted the older idea that the earth was made up of 4 elements, earth, water, air, fire, but assumed that the heavens were made of a quite different 5th element, quintessence. They admitted that the earth was changeable, but insisted that the celestial areas were rigidly unchanging. They claimed that the laws of motion in the two were quite different. Objects on the earth moving naturally in straight lines at decreasing velocity to their natural condition of rest, while objects in the heavens moved in perfect circles at constant speed as their natural condition. These non-scientific assumptions, made about 400 BC without proof and by violating the fundamental rules of scientific method, set up a non-scientific worldview which could not be disproved. The Pythagorean rationalists were able to do this and to destroy science because the scientists of that day, like many scientists of today, had no clear idea of scientific method and were therefore in no position to defend it. Even today, few scientists and perhaps even fewer non-scientists realize that science is a method and nothing else. Even in books pretending to be authoritative, we are told that science is a body of knowledge or that science is certain areas of study. It is neither of these. Science clearly could be a body of knowledge only if we were willing to use the name for something that is constantly changing, from week to week, even from day to day. The body of knowledge to which we attribute the name science is changing. The beliefs of one day being, sooner or later, abandoned for quite different beliefs. Closely related to the erroneous idea that science is a body of knowledge is the equally erroneous idea that scientific theories are true. One example of this belief is the idea that such theories begin asterisk as hypotheses and somehow are proved and become laws. There is no way in which any scientific theory could be proved, and as a result, such theories always remain hypotheses. The fact that such theories work and permit us to manipulate and even transform the physical world is no proof that these theories are true. Many theories that were clearly untrue have worked and continue to work for long periods. The belief that the world is a flat surface did not prevent men from moving about on its surface successfully. The acceptance of Aristotelian beliefs about falling bodies did not keep people from dealing with such bodies, and doing so with considerable success. Men could have played baseball on a flat world under Aristotle's laws and still pitched curves and hit home runs with as much skill as they do today. Eventually, to be sure, erroneous theories will fail to work and their falseness will be revealed, but it may take a very long time for this to happen, especially if men continue to operate in the limited areas in which the erroneous theories were formulated. Thus, scientific theories must be recognized as hypotheses and as subjective human creations, no matter how long they remain unrefuted. Failure to recognize this helped to kill ancient science in the days of the Greeks. At that time, the chief enemies of science were the rationalists. These men, with all the prestige of Pythagoras and Plato behind them, argued that the human senses are not dependable but are erroneous and misleading, and that, accordingly, the truth must be sought without using the senses and observation, and by the use of reason and logic alone. The scientists of the day were trying to reduce the complexity of innumerable observed qualities to the simplicity of quantitative differences of a few fundamental elements. This is, of course, exactly what scientists have always done, seeking to explain the subjective complexity of qualitative differences such as temperature, color, texture, and hardness in quantitative terms. But in doing this, they introduced a dichotomy between appearance and reality that became one of the fundamental categories of ancient intellectual controversy. All things, as the scientists said, may be made up of different proportions of the 4 basic elements: earth, water, air, fire, but they certainly do not appear to be. The same problem arises in our own day when scientists tell us that the most solid piece of rock or metal is very largely made up of empty space between minute electrical charges. The Pythagoreans argued that if things are really not what they seem, our senses are at fault because they reveal to us the appearance, which is not true, rather than the reality, which is true. This being so, the senses are undependable and erroneous and should not be used by us to determine the nature of reality. Instead, we should use the same reason and logic that showed us that reality was not like the appearance of things. It was this recourse to rational processes independent of observation that led the ancient rationalists to assume the theories violating Occam's razor that became established as Aristotelian and dominated men's ideas of the universe until, almost 2,000 years later, they were refuted by Galileo and others who re-established observation and Occam's razor in scientific procedure. The third part of scientific method is testing the hypothesis. This can be done in three ways: U, by checking back; Z, by foretelling new observations; and C, by experimentation with controls. Of these, the first two are simple enough. We check back by examining all the evidence used in formulating the hypothesis to make sure that the hypothesis can explain each observation. A second kind of test, which is much more convincing, is to use the hypothesis to foretell new observations. If a theory of the solar system allows us, as Newton's did, to predict the exact time and place for a future eclipse of the sun, or if the theory makes it possible for us to calculate the size and position of an unknown planet that is subsequently found through the telescope, we may regard our hypotheses as greatly strengthened. The third type of test of a hypothesis, experimentation with controls, is somewhat more complicated. If a man had a virus he believed to be the cause of some disease, he might test it by injecting some of it into the members of a group. Even if each person who had been injected came down with the disease, the experiment would not be a scientific one and would prove nothing. The persons injected could have been exposed to another common source of infection, and the injection might have had nothing to do with the disease. In order to have a scientific experiment, we must not inject every member of the group, but only every other member, keeping the uninjected alternate members under identical conditions, except for the fact that they have not been injected with the virus. The injected members we call the experimental group. The uninjected persons we call the control group. If all other conditions are the same for both groups, and the injected experimental group contract the disease, while the control group do not, we have fairly certain evidence that the virus causes the disease. Notice that the conditions of the control group and the experimental group are the same, except for one factor that is different: the injection. A fact allowing us to attribute any difference in final result to the one factor that is different. The nature of experimentation with controls must be clearly understood because it has frequently been distorted from ignorance or malice. A number of years ago, a book called Science is a Sacred Cow made a malicious attack on science. In this work, the method of experimental science was explained somewhat like this. On Monday, I drink whiskey and water and get drunk. On Tuesday, I drink gin and water and get drunk. On Wednesday, I drink vodka and water and get drunk. On Thursday, I think about this and decide that water makes me drunk, since this is the only common action and I did every day. This perversion of scientific method is the exact opposite of a scientific experiment. In this performance, we assume that all conditions were different except one, and attributed cause to the one condition that was the same. In scientific method, we establish all conditions the same except one, and attribute causation to the one factor that is different. In the perversion of scientific method, we made an assumption that was not proved, and probably could not be proved, that all conditions, except drinking water, were different. And then we tried to attribute causation to the one common factor. But there never could be only one factor the same, since as an experimental animal, I was breathing air each day, and doing a number of other common actions, including drinking alcohol. There would perhaps be no reason to pay attention to this perversion of science if it were an isolated case. But it is not an isolated case. Indeed, the book in question. Science is a Sacred Cow attracted undeserved attention and was publicized in America's most widely read picture magazine as a worthy book and a salutary effort to readjust the balance of America's idolatry of science. The magazine article in question reprinted extracts from the book, including the section on experimental method, and seriously presented to millions of readers the experimental proof that water is an intoxicant as an example of scientific method. Scientific method as we have presented it, consisting of observation, making hypotheses, and testing, is as applicable to the social sciences as it is to the natural sciences. To be sure, certain variations in applying it to the social sciences are necessary. But this is equally true of various parts of the natural sciences. These variations are most needed in testing hypotheses. Even in the natural sciences, we frequently cannot use two of the three kinds of testing. We cannot use forecasting in the study of earthquakes or geology in general. We cannot use controlled experiments in these fields or in astronomy. But these deficiencies do not prevent us from regarding geology or astronomy, seismology, or meteorology as sciences. Nor should similar deficiencies, especially difficulty in forecasting and the impossibility of controlled experimentation, prevent us from applying the scientific method to the social sciences. The applicability of scientific method to the study of society has also been questioned on the ground that theories of the social sciences are too changeable. We are told that every generation must rewrite the history of the past, or even that every individual must form his own picture of history. This may be true to some extent, but it is almost equally true of the natural sciences. Science is a method, not a body of knowledge or a picture of the world. The method remains largely unchanged, except for refinements, generation after generation, but the body of scientific knowledge resulting from the use of this method or the world picture it provides is changing from month to month and almost from day to day. The scientific picture of the universe today is quite different from that of even so recent a man as Einstein, and immensely different from those of Pasteur and Newton. And even at a given moment, the body of knowledge possessed by any single scientist or the world picture he has made from that knowledge is quite different from that possessed by other scientists. Yet such persons are all worthy to be called scientists if they use scientific method. The same is true in the social sciences. The one major difference between the natural sciences and the social sciences is the assumption, made in the former, that human thoughts cannot influence what happens. This is an assumption justified by the rule of simplicity, although few persons recognize that it is. There is a considerable body of evidence that human thoughts can influence the physical world, but this evidence, segregated into such fields as parapsychology or the psychic world, is not acceptable to the natural sciences. As a result, phenomena such as poltergeist manifestations, largely because they cannot be repeated on request, go unexplained and are generally ignored by the natural sciences. The latter continue to assume that physical processes are immune to spiritual influences. In the social sciences, on the other hand, it is perfectly clear that human thoughts can influence what happens, and accordingly, the social scientist must face the more complicated situation created by this admission. Thus, we assume that a rock dropped from a high window will fall even if everyone in the world expected it to rise or wanted it to rise. On the other hand, we are quite prepared to see the price of General Motors common stock rise if any large group of people expects it to rise. In a somewhat similar fashion, expectation of a war or desire for a war will make war more likely. This difference between the social sciences and the natural sciences makes it possible to draw up fairly definite conditions, distinguishing between the two. The natural sciences are concerned with phenomena where we do not expect subjective factors to influence what happens, while the social sciences are concerned with phenomena where subjective factors may affect the outcome. In this book, we are concerned with the social sciences thus defined, and particularly with the effort to apply a scientific method of observation, formulation of hypotheses, and testing to such phenomena. The enormous size of this field has made it advisable to curtail our attention to the process of social change, especially in civilizations.